Hi, thank you very much for the opportunity. I'm from Arizona at Stewart, working as a postdoc at Stewart Observatory. So I will talk about MAPS project. We are building adaptive optic system for MMT. Several collaborations. PI is Katie Morzinski, and Suresh Sivanandam from Toronto is also collaborating. So this project is a 4-year NSF MC project funded to upgrade MMT adaptive optic secondary mirror, which was old and it was not working since I think 2 years because of leakage of oil and the system in the past used Shakatman and it emits a lot of power, so it was not very optimized. So the money was given to upgrade this adaptive optic secondary mirror and also to upgrade the science camera. The science camera is Arizona infrared SLA spectrometer. It has imager and spectrograph. And so it is being upgraded to 60,000 spectral resolution. So when it is built, it looks like Criris, but in northern hemisphere. So 60 nights are committed. So those will be used to characterize exoplanets, their atmospheres. So this is the MMT telescope located in Arizona, Mount Hopkins mountain. And so this is the secondary adaptive secondary mirror, which is currently installed in the lab, and our team developed these actuators and control and software. So this is optimized for low power emission, and also this can able to correct higher modes, like it has now 336 actuators. So the ASM will be installed it's a secondary mirror, so it is installed here. And I'm going to talk about the wavefront sensor. We have two wavefront sensor, visible and pyramid, visible wavefront sensor and IR wavefront sensor to maximize the natural gas star sample. So these are the science cameras sit here. And we communicate with wavefront sensor with camera link cables to the computer, and from the reconstructor computer to the ASM using Ethernet cable. So the optical design done by Oli Dorney, and so the light comes from the telescope, and input triplet lens images the F15 beam into F50 on the pyramid wavefront sensor, and this is the atmospheric differential conductor, and then a part of the visible light lower wavelength before 0.6 micron that goes to the acquisition camera. And then the remaining light goes to the this channel, and visible 0.6 to 1 micron goes to the visible wavefront sensor, and part of the J band light or high band light goes to the IR wavefront sensor. It is this one is developed by Toronto team. They use a Saphira detector. So yeah, the pyramid wavefront sensor is explained in previous talks, but I want to highlight, I'm going to talk about the modulator using a tip tilt mirror. And basically the telescope light is focused on the pyramid, and then that is the pyramid samples the pupil image on the detector. So from the quad cell, we measure the slopes. It's very standard. So the visible pyramid wavefront sensor is designed by Oli Dorney, and currently it is in the procurement. So we expect to deliver by, it is delayed, we expect to deliver by November. So we use the design of LBT, but it is optimized for MMT. So the first design is taken from LBT. So the key parameters are, we use 30 by 30 kind of Shakatman. So 30 pixel lenslet kind of thing. And then the separation between each quadrant is 39 microns. The wavelength of operation is 0.6 to 1 micron. So we modulate lambda by 5 lambda by d modulation to increase the uh, dynamic range. We use a CCID 75 a camera which was given by Air Force to one of our colleague, Gerard Mills. And this camera is very good in the readout noise and is also fast by using two frame transfer storage areas. So the full, the size of the detector is 116 to 160 pixels. Since we have require only like 80 pixels we require for our all four quadrants. So the quantum efficiency, I just want to mention, this is very good in the visible part, and it has several actual 32 programs to select, and I will show you in the next slide which one we select. So this is installed in the lab, and we already read the frames from the camera, and this is a scene image, and this is the bias image we use. Yeah, this camera uses side measure controller, and we use EDT frame grabber to get the frames from the camera, and the distance between the camera and computer are extended with camera link cables. So we did photon transfer curve to estimate the readout noise and the gain of each program. We have 32 choices. So I'm showing you the best choice of better readout noise case. So we get like 2.73 electrons per second readout noise. So it is not EMCCD, and that is one of the advantages if you operate in photon noise regime. So we plan to use this program, so which is we get like 2.77 electron per pixel, and we will operate 1 kilohertz frame rate. We have also installed in the lab a tip tilt modulator. So we use a PI controller-based E727 controller, which modulate the mirror in sine and cosine waves with offset of 90 degrees. So this is this has the input and output channels to synchronize with the CCD 75 frames to synchronize the frames with the modulator. So, and also this is a powerful when we, so this is the frequency response. So when we go from 10 hertz to 1000 hertz, the modulation amplitude is not decreasing very much. So for this is, we think this is the safest way. So 10 lambda by D for the infrared wavefront sensor, but for the visible, it's 5 lambda by D. So our requirement is 1428 microradians, but we can go more than 2 times than that. And this is the modulation circle we made, and so these bigles are corrected already, but it's a old picture, but the circular, so it's not kind of, it looks like a little bit elliptical that we need to correct it. And we have 3 computers. One is for wavefront sensors. So all wavefront sensor cameras, visible and IR wavefront sensor and acquisition camera are connected to one computer, and the software is already written. And so another computer that is reconstructor computer, which always try to get the slopes from the one of the camera, which is opted for the signs based on the reading of the star. So we have 2 loops. One is inner loop it always works inside the reconstructor and the ASM, and another one is we get the slopes from this one. So current status, we have the wavefront sensor camera is working, and we measured all the characterization of it, and we also almost finished the tip tilt modulator characterization. We are waiting for the pyramid to test in the lab. So so that helps us to fit everything, install everything, and check all the components of the wavefront sensor. So we try to compare the performance of the wavefront sensor, the adaptive optics output still ratio. For CCID 75, we get almost like close to 70% for magnitudes of 10 NGS stars. Yeah, this is the status. Thank you.
Thank you very much. So I think we don't have any time for questions, but again, in Slack, if you have any, do not hesitate to ask.